So we're going to continue on the concept of rate of change and instantaneous rate of change, which is bringing us into the next section, which is the derivative. And so recall the rate of change, if we were looking at a graph, we have some function. And if we wanted to find the rate of change between 2 points, let's say A and B, we would find our point on the graph. So when x is a, we would plug that into whatever our function is, and let's call our function f of x. And when we plugged in a, wherever we saw an x, if we had the equation, the y value is f of a. And then and x equals b, we would find the point on the graph. We would look at the y value when x was b. And one of the ways that we could write that y value when x is b is f of b. And so when we're looking at this average rate of change, we're looking at the slope of the line that joins those two. So the average rate of change between x equals a and x equals b is the change in our y value, so f of b minus f of a, all over the change in our x value, so b minus a. So that's pretty much just the slope. That is the slope between 2 points on that line. And then we looked at the instantaneous rate of change. And so far in our mathematical careers, we've been able to find the slope if we're given a line. If the equation we're given is not a line, then we do not know how to find the slope. We can say, look at the graph, we could tell where it's increasing, decreasing, maybe where it's increasing faster than other places, but we couldn't actually tell what that slope of the line was at one particular value. We could do what we had just done and found an average rate of change between two particular values and kind of get an idea what that slope is. So with calculus and with limits, we can now find the rate of change or instantaneous rate of change at any particular value. And so let's say, again, we have some graph f of x. We have some value here, a. And let's say we wanted to find the instantaneous rate of change right here. We want to know what is that slope at that particular point on that graph. And so we could, choose another point, like I said, over here, and we could find that average rate of change. But notice if I choose a point even closer than this one, how about I come over here and I choose this point? Well, if I find the slope between those 2 points, that's going to give me a better estimate than the ones that I had chosen over there. So even getting closer is even better. So basically what we're doing is we're saying, okay, we have our value of x equals a, and we're going to choose some distance getting really, really close to a. So let's just add a little increment to that value x equals a, and we're going to call it h. And we're going to make this h value smaller and smaller. We're going to have it get closer and closer to a, infinitesimally small. And when we're doing that, we can say, okay, well, then we have the instantaneous rate of change right at x equals a. And so let's write that out. So if we're having a point, we have a point when x is equal a. We have a point when x is equal to a plus that little value that we're adding to it so that we can find that rate of change. And so the point when x is a is a f of a, right? Another way to write y when x is a. And this point here, when x is a plus h, our x value is a plus h, and our y value is f of a plus h. And so if we now take the slope of that, so the change in our y value, f of a plus h, minus the change, minus f of a, all over the change in our x value. So I started with a plus h, this point. So a plus h here minus this x value, a. The thing is, we want this h value to be very, very small, getting closer and closer to a. And in order to get closer and closer to a, this value of h has to approach 0. And so we can write the limit of this as h approaches 0. And this is our instantaneous rate of change. Of f of x at x equals a. Okay, so I'm going to just kind of bring in the next section while I'm going over the rest of this section and giving you examples. So the next section talks about the derivative. And the derivative is basically what we are just doing, finding the instantaneous rate of change. They're interchangeable, different ways to say the same thing. Okay, so the derivative of a function f at x equals a is this limit as h goes to 0 of f of a plus h minus f of a all over. And I just noticed up here that I didn't simplify my numerator and my denominator. Notice that a plus h minus a, those a values cancel out. So we can simplify that. And this would just be over h. So it's really equal to the limit as h goes to 0. F of a plus h minus f of a all over h. And if we're looking at the derivative and we find that slope at some particular value, so in this case, x equals a, the line that goes through this point and has the slope at this point, so it would look like this. This is called the tangent line. So let me just write that down. So the tangent line is the line, let's say the tangent line at x equals a is the line that goes through the point at x equals a. So that would be a f of a and has the slope which is equal to the instantaneous rate of change at x equals a. So it has the slope that is equal to the instantaneous rate of change. At x equals a. Okay, so if you are looking at a tangent line, depends on where you're on the graph. And so if you're trying to figure out what that tangent line is going to look like on the graph, so choose some point on the graph. I kind of think of it as, okay, if I was driving on this at night and I had my headlights on, what way would my headlights be pointing? So right here, right, my headlights would be pointing this direction. And so that's basically what the tangent line would look like at this point here. If I was driving over here, right, and always going left to right, funky car, my car is not pointing the right way. It's going to be pointing this way, right? If I'm at this point, my headlights would be pointing this way. If I came over here and I was driving, my headlights are going to be pointing upwards, right? So these are all tangent lines at particular points on x equals a. So right here, my headlights would be pointing this way. Down here, they'd be pointing this way. Okay, so those are what our tangent lines are going to look like. And so we're going to be finding these equations of the line. And we'll talk about finding the equation of the line again, and I'll review how to do that when we get to that point. One other terminology that you need to know are your secant lines. So secant lines, those are the line that joins the 2 points when you're looking at the average rate of change, not the instantaneous rate of change. So your secant line is the line on the graph that joins 2 points on f of x and has the slope has the same slope. Or the average rate of change. Between x equals a and x equals b. On our function. Okay, so if we had some graph and we wanted to find the secant line between a and b, let's say a was here, b's out here, we would look at these 2 points on our line or a graph, we would join the 2 points and make a line. And then in here, this line is called the secant line. So let's go and do one more example, at least, for finding the average rate of change. Then let's look at finding the instantaneous rate of change of a function at a particular point. Let me just pause the video for a sec. Okay, so we're looking at an example, finding the average rate of change of y equals e to the x between x equals -2 and 0. So recall e is just an irrational number, kind of like pi, and this is 2.81, I believe, 7 ... Goes on forever. I don't think I'm wrong, so I have to check. 2.718. I knew something was off on that decimal. Okay, so it's just a number. So basically think of this is an exponential function. If we were to look at, I just want to kind of look at the graph there. Our exponential function looks similar to this. And it's asking us, okay, we want to find the average rate of change between x equals -2. So let's go down to x equals -2 on our graph. And x equals 0. So when x is 0 here, we have a point here. And so we want to find the equation or the slope between these 2 points. So we need to figure out what those points are. And so when x is equal to -2, we need to figure out what our y value is. And so when x is equal to -2, y would equal e to the, plugging in -2, where you see an x in the function, -2. So we have a point at -2, comma, e -2, raised to the -2. And so when x is 0, y is equal to e raised to the 0 power. Well, a number other than 0 raised to the 0 power is 1. And so this is equal to 1. And so we have a point when x is 0, our y value is 1. And so now we want to find the slope between these 2 points. So we're looking at the change in our y value, 1 minus e to the -2 power, all over 0 minus -2. Okay, so let's simplify that a little bit. And so we have 1 minus e to the -2 all over a negative and a negative, so that's +2. So if you were to throw this in the calculator, you need to be careful of, if you're going to put it in all at once, that you need parentheses around certain things. And so in the calculator, you're going to put parentheses around the whole numerator, 1 minus. You should have some E button on your calculator. You might have a caret like this next to it, or actually when you push it, you'll see that caret. And then you're going to put parentheses, make sure it's the negative, not the minus sign, -2 in that parentheses, divided by 2. So if you do that, you should get about 0.4323. Okay, so the average rate of change on this graph, y equals e to the x, is, yeah, I don't think you guys can see my cursor when I'm doing it. So average rate of change of that function between these 2 points is the slope of the line that joins them. We can also say that this is the slope of our secant line. And y equals e to the x at x equals -2 and 0. So now let's say they wanted us to find the instantaneous rate of change at x equals 0. So let's look at the same example, but now let's look at the instantaneous rate of change. So we have an example, and we want to find the instantaneous rate of change at x equals 0 on the graph. Let's call it f of x equals e to the x. So let's look at that. So we want to find exactly what's happening when x equals 0. So recall, we looked at the definition. Let's rewrite that. So instantaneous rate of change, we're looking at the limit as h goes to 0 of f of a plus h minus f of a all over h. Our value in this case, our a value, is 0. So a equals 0 in this example. So let's go through and let's look at the following. Let's look at f of 0 plus h. So if we go in, this is saying go in, and that's the same thing. Let's just reduce that. This is the same thing as f of 0 plus h is just h, right? So we're going to go into our function f of x, and wherever we see an x, we're going to replace that with h. And so we have e, that's raised to the x power. So instead of writing the x, we're going to replace it with the h. Okay, so far we have the limit as h goes to 0 of this piece, which we just found to be e to the h power, minus f of a. So again, a in our case is 0. So we need to find f of 0. So we're going to go in, and wherever we see an x in our function, e to the x, we're going to replace the x with a 0. So we have e raised to the 0 power, which we talked about, e to the 0 is 1. So minus this EF of the 0, which we just said was 1, all over this value H. Okay, so this is finding the instantaneous rate of change when X is equal to 0. So you're going to have some problems like this on the homework. And right now, how we're going to deal with this is we need to use either a graphing calculator or some calculator to help us. And so if you don't have a graphing calculator, which you don't need one for this class, you can use Desmos. So let me teach you how to do that. So to help you, you can go to desmos.com. When you get here, you can graph functions using the graphing calculator, but I want it to do some algebra for me by plugging in values, H values, which are close to 0. And so I'm going to go to their math tools, and I'm going to go to the scientific calculator. So we're going to define our function. And so we had just said that we had gotten the instantaneous rate of change to be e to the h minus 1, all of that in the numerator. So in order to define this so that it will plug in stuff, maybe call it f of h. For some reason, my keyboard's not working. There we go. Okay, so f of h, really? Let me pause while I get this to work. Okay, so f of h, let's call that our function because I'm going to use the variable h instead of x, is equal to, in our numerator, we have e, it was raised to the h power. Then we had a minus 1, and then divided by h. Okay, so this was our formula to find the instantaneous rate of change. This is how far we got. So once you plug in your formula, push enter. And now we want to evaluate this. So remember, we're having values of h getting closer and closer to 0. And so let's look at what is f of 0.1. That's pretty close to 0. And what you want to do when you're working this type of problem on My Math Lab, come to desmos.com, or you can use your graphing calculator if you have one. You want to do this until you get up to numbers that are repeating itself 2 times. And so f of 0.1, I see I get 1.05. So let's get a number even closer to 0. So let's put f of 0.01. Okay, notice here I have 1.0. Those two numbers are the same, but this 5 and the 0, so 2 places after the decimal, is not the same. But it looks like it might be getting closer and closer to 1. Let's see. So now if I plug in f of 0.001, okay, so now look at that. This is the 2 decimals places after are the same. And so we can say, and you can get closer, that this is approximately 1.00. And so our instantaneous rate of change is equal to 1.00. Okay, so what is that saying again? Is if we looked at our graph of our function e to the x, which looks something like this, at x equals 0, if I was looking at the tangent line, so kind of think again about the car driving, what way would your headlights be facing? at night, be going out this direction. That's the slope of this tangent line. Is the slope of the tangent line, but it's also the slope at this particular point, x equals 0 on that graph. Okay, so then that is 3.3, average rate of change, instantaneous rate of change. We started getting into a little bit of 3.4 in our textbook, which is talking about the derivative, the secant line, and the tangent line. So maybe change videos and let's jump into what the derivative is, which we basically just did with the instantaneous rate of change.